Welcome back to The Foundry by Forge College. I'm your host, and today we're rolling out the engineering blueprint to see exactly how distributed systems are actually built. This explainer is a pretty critical piece of our blockchain fundamentals track, specifically for the Understanding Distributed Ledger Technology module. So grab your hard hats because we're getting mechanical today.
Okay, let's take a quick look at today's agenda. We're going to cover the core design challenge, copying data, dividing data, the consistency trade-off, surviving failures, and finally, we'll be designing a real ledger together. Let's just dive right in.
Section 1. The Distributed Design Challenge.
Building on our previous lesson about the history and evolution of these networks, we all know decentralization is essential, right? But now, we've got to confront the actual mechanical challenge of building it. The crucial thing we're solving today is figuring out which specific architectural knobs we can turn to perfectly balance performance, correctness, and complexity. I mean, we know why engineers wanted to ditch those single, centralized mainframes, but when you spread your data out across dozens, hundreds, or even thousands of nodes, well, suddenly you aren't just an engineer anymore. You're orchestrating absolute chaos. How do you ensure everyone agrees? How do you keep it blazing fast without the whole system literally catching fire? That right there is the core design challenge of distributed systems.
All right, Section 2, Copying Data, otherwise known as replication strategies. So replication just means copying data across nodes so you can survive failures and crank up your read throughput. And there are three main ways to handle this. Think of the single leader strategy like a head chef shouting orders in a kitchen. Everyone listens to one person, which ensures perfect order, but hey, if that chef loses their voice, the whole kitchen stops. Then you have the multi-leader strategy. That's more like a potluck dinner where everyone brings dishes. It's highly available for sure, but conflicts are definitely going to happen when 3 different people bring potato salad and you have to awkwardly reconcile that later. And finally, the leaderless strategy. That's like a group vote on where to eat. You distribute the rights and rely on a quorum or a majority agreement to make sure you land on the right answer.
And when you look at these options side by side, it reveals a constant set of trade-offs. Just look at that operational complexity column. Listen, there are no perfect solutions in distributed systems, only trade-offs you're willing to live with. For instance, choosing multi-leader massively boosts your system's availability since anyone can accept a write, but it completely forces you into high operational complexity to resolve those data conflicts. Single leader, on the other hand, makes reasoning about correctness so much easier, but it creates a total bottleneck at the leader. You basically got to pick your poison.
Moving on to Section 3, Dividing Data, or Partitioning explained.
So if replication is making copies of your data, partitioning, which you'll often hear called sharding, is splitting your massive data set into smaller, much more manageable chunks. We have 2 main approaches here. Hash-based partitioning is kind of like dealing cards randomly to players using a math function. It gives us this perfectly even spread of data across all our nodes, but actually finding a specific sequence of cards later, total nightmare. Range-based partitioning, on the other hand, keeps things in alphabetical or numerical order, like volumes of an old encyclopedia. This makes scanning a range of data super simple, but you risk creating hotspots. Imagine if suddenly everyone in the world wants to read the letter S at the exact same time. You're going to completely overload a single node.
Which reads perfectly into Section 4, the consistency and latency trade-off. Because we're dividing and copying all this data across different physical machines, we have to define strict rules for consistency, and this brings us to our ultimate goal in many financial systems, strong consistency. Achieving this means your system behaves predictably. It essentially gives you the illusion that there's only one copy of the data. If you deposit $10, the very next read will show that $10, no matter which node you ask. But, and this is a massive but, the trade-off is that the synchronous coordination required to actually guarantee this drastically increases your write latency. You literally have to sit and wait for the nodes to talk to each other across a network before confirming the transaction.
Alternatively, if you go the leaderless route we discussed earlier, you rely on this floating quorum equation. R stands for read nodes, W stands for write nodes, and N is the total nodes. The golden rule here is that your read nodes plus your write nodes must be strictly greater than your total nodes. So if you have 5 nodes total and you write to 3 of them, you absolutely must read from at least 3 of them to guarantee an overlap. That overlap is exactly what ensures you aren't reading still data. It's just a really elegant mathematical balancing act between speed and correctness.
All right, Section 5, Surviving Inevitable System Failures.
As any seasoned engineer knows, servers are going to catch fire, random backhoes will somehow sever your fiber optic cables, and networks will just snap. In our advanced courses and programs at Forge College, we actually build Python simulations of these exact steps to show how a single leader system serializes writes and manages follower outages. When a follower node fails, the leader detects it via a timeout. The leader then has to make a split-second decision. Do we fail the entire write to maintain strict consistency, or do we proceed asynchronously just to keep the system available? Later on, when that broken node finally comes back online, background threads run what we call anti-entropy repair. Sounds like a sci-fi movie, right? To clean up the mess and sync the data back up.
The crucial takeaway here is that you must explicitly design for failure. A distributed system might look absolutely beautiful and theoretically sound on a whiteboard, but a system that looks correct in a steady state can behave wildly during a failover. If you haven't explicitly planned your recovery paths, your users are going to be the ones experiencing that chaos firsthand.
Let's move to our final section and see how this all builds into something practical, designing a real ledger. Okay, let's put on our hard hats and apply these theoretical patterns to a concrete, real-world scenario. We're going to design a global ledger service. Let's look at the absolute constraints for our project. First, we need strict per-account transaction ordering. Second, we can have zero loss committed writes. This is people's money we're talking about here. 0 is the only acceptable number. Third, we need high write throughput across totally different geographic regions. And finally, we must be able to survive a full data center outage. Now, if we have a ledger where strict ordering and zero lost writes are mandatory, we just cannot risk the conflicting data of a multi-leader potluck, and we definitely can't risk the slightly stale reads of a leaderless vote.
So to meet those strict constraints, option A is our absolute best path. We use hash-based partitioning to evenly distribute the accounts, and we pair it with single leader's synchronous replication. By doing this, we're actively trading higher cross-region write latency, meaning transactions take a fraction of a second longer to confirm, in exchange for straightforward correctness and rock-solid per-account ordering. We happily accept that latency hit because losing a transaction is an entirely unacceptable failure for the specific architectural blueprint.
And that brings us to the ultimate question for any system builder. The next time you look at a Web3 protocol or a decentralized architecture, I want you to ask yourself, what trade-offs did they make? Thanks for exploring this explainer with us. To dive deeper into these mechanical trade-offs, practice your own system design, and learn a whole lot more about this subject and other Web3 topics, definitely go check out forge.college. I'll see you in the next explainer.